In this session, this is probably going to be the first of 4 sessions. The video that we're going to use currently is about 25 minutes long, but I anticipate that I will, as we go through here, I'll stop and make some comments along the way. And since these need to be in sections or sessions that are less than 10 minutes long, I'm probably going to go over the 30 minutes, but at this time I don't know. Let me go ahead and let's get started with this discussion of regression and correlation. These are two different but related topics. Regression is often used to determine the relationship, the mathematical relationship between two variables. A lot of times you get a formula out of it. And correlation is used to measure the strength of that association or that agreement. In correlation, we use a thing that's called R, Pearson's R. It's called the correlation coefficient, and it's the amount of the measure of the amount of agreement or the strength of the relationship, the strength of the association between the two variables. It's a value between -1 and 1. R squared is going to be the proportion of the variation in y that's explained by the linear relationship between x and y. Now, we need to understand that we're talking about linear. That's in a line. Nonlinear relationships do exist. For example, if we were to measure the arm strength by age, then in the early years it'd be low, and in the older years it'd be low, but it would be higher in the mid-years. So for example, if we were to have our age go across this way, 0 to say 70, and then our strength, however we want to measure it, whether you're, this is arm strength, so how many pounds you can lift with one arm. Well, a baby, of course, can't lift a whole lot. But once you get up to be, 18, 19, 20, you might be able to, gradually get up to the point where you can reach, where you can lift, 50, 60, 70 pounds. And then as you get older, then it would decrease to some point. Okay? That is not a linear relationship, but there is a relationship there. You could define that relationship. If we were to go and plot this, then we would find that maybe the linear relationship goes straight across like this. And so our R here would be equal to 0 or close to that. And it would say that there's no relationship between age and arm strength. But when in reality there is one. It's just that it's not linear. So it's very important in this discussion to understand that we are talking about a linear relationship. Okay, an example. So if R is equal to 0.01, then R squared is going to be this squared, so it's going to be, when I say 0.01, 0.08. R squared is going to be 0.08 times 0.08, which is going to be 0.64. Thus, 64% of the variability in y is explained by the linear relationship between x and y. We get to the point where R is equal to 1, then R squared is equal to 1 or 100%. So if we get to the point where R is equal to 1, then 100% of the variability can be explained. If 100% of the variability can be explained, then everything can be explained. if we have an R that's negative, a -1, then it's a negative relationship. If it's a 1, it's a positive relationship. If R is equal to 0, there's no relationship. In a plot, you'll see if something goes like this, that's negative. If something goes like this, line goes like that, it's positive. And if it goes straight across, then that means that there is no relationship. Okay? But remember, we're talking about a linear relationship. And nonlinear relationships do exist. So let's look at regression. This is if you've done algebra, geometry, those guys. Let me break in at this point right here and give you just a quick table that you may see in the textbook. Again, it's a comparison of these values and the R value with the strength of the relationship. And these are commonly used. You can see that here that an R value of 1, and these could be positive or negative, has got an R squared of 1.0, which is called perfect. You get down to a 0.70 and R squared is 0.49, so that's about half of it. That's a moderate relationship. You get down like a 0.2 and R squared would be 0.04, so that's a relatively negligible relationship. We're going to find out when we start looking at the table on these is that if you have a large sample size, like 1,000, then these values down here can be significant. But practically, if you can only explain 0.01, or you can only explain 100th of the variability or 1% of the variability, then practically this is not very much of a relationship. So although a relationship of 0.4 could be significant statistically, the 0.16 or 16% of variability explained is going to be low. So let's go back to the video and pick up at that point. Things, Trig, you'll know that y is equal to b0 plus b1 x. Okay, this might be, sometimes you may see this y is equal to mx plus b. Okay, we just sort of change these around. B1 is the m, and b here is the b sub 0. In either case, the m or the b1 is the slope of the line, and the b0 or the b in this situation is the y-intercept. That means that where it goes across, this is the x-axis and this is the y-axis. Where it goes across the y-axis, that's the y-intercept. As we mentioned earlier, a positive slope goes up and a negative slope goes down. I want to interrupt again, just right here at this, just for a second here at the end of this session, and let's just do a couple of examples here. Let's say that y is equal to 5x plus 10. Okay, this would be the slope. This would be the intercept. Okay, if we have y is equal to minus 2x minus 8, again, a negative slope, which would mean that it goes down. On the positive slope up here with 5, that's going to go up. Change these things around, and you could have something like y is equal to 0.5x plus 10 or something like that. Again, this is the slope and that is the intercept. So I'm going to end this one. This is the the first session in this, and we will start the second session right where we ended just a minute ago.